In this video, we are finally going to prove the theorem that if f of x and g of x are primitive polynomials in z adjoint x, then the product of f of x and g of x is primitive. All right, so here's the proof. Let's start by giving names to the coefficients of f of x and g of x, and also of f of x times g of x. So let's let f of x equal ak x to the k plus ak minus 1 x to the k minus 1, and so on, down to a1 x plus a0. Let's let g of x equal bl x to the l plus bl minus 1 x to the l minus 1, and so on, down to b1 x plus b naught. Notice that the degree of g may be different from the degree of f. We're also going to stipulate, by the way, that a sub k is non-zero and b sub l is non-zero, so that the degree of f of x and of g of x are exactly what it looks like, k and l respectively. And then we're going to let f of x times g of x equal cm x to the m plus cm minus 1 x to the m minus 1, and so on down to c1x plus c0. And we will also stipulate c of m is not equal to 0, which means that m is going to equal k plus l. All right, not that we'll necessarily use all of those things later, I just want to have them in place. All right, so here's the game plan. We're going to let p be a prime number, and we're going to show p doesn't divide all of these coefficients, all of c0, c1 through cm. Because once we show that, that means p will not divide the GCD of c0, c1 through cm. So in other words, p doesn't divide the content of f of x times g of x. Okay, and if the content of f of x times g of x is not divisible by any prime, then what does it have to be? So the content of f of x times g of x won't be divisible by any prime, so it must be 1. So that's how the argument's going to work. We're going to fix a prime p and focus on that, but really the argument we use on p is going to be something that works for every prime. So once we know it works for every prime, we will know that for any given prime, there will be some coefficient in here that is not divisible by p. And then once we know that, we will know that there is no prime which divides all of these, therefore the content of this polynomial has to be 1, therefore f of x times g of x is primitive. Alright, so since we've already fixed a prime p, I'm going to zoom out, just give us some room to work here. A little bit more, we're going to keep the polynomials visible in frame, but I want to have a big diagram over here on the right, just to remind us of the reasoning we did in the last video, because I thought that was helpful. Alright, and I realize that my line drawing on this thing is not the best, but I hope you'll bear with me. So let's make a few lines down here, a few cells, and then a few cells up here. There we go. And let's have a few cells over here. Fill that in. Alright, there we go. Alright, sorry, this looks like the array multiplication from The Simpsons, but hopefully that'll help. Alright, so down here I'm going to put f of x, and I'm going to put the terms of f of x here. This is going to be ak x to the k, ak minus 1 x to the k minus 1. And then I put a bigger space here, so we go dot, 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 and then a2x squared, a1x, a0. Up here I'm going to have g of x, and the terms of g of x go bl x to the l, bl minus 1 x to the l minus 1, and then dot, 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 b2x squared, b1x, and then b0. And I'm not going to bother filling in all of these. In fact, I'm not even going to bother filling in any of these. You can imagine what would go in each cell. And I don't have a lot of room to write, so I'm going to avoid filling those out. Instead, I'm just going to use this as a visual diagram of what's happening in the proof in terms of divisibility by p. So you might remember last time we used our little highlighter to indicate terms of each polynomial which were divisible by p. In the video it was 3, but here we're going to say p. Alright, so let's say in this polynomial f of x, I have some terms which are divisible by p, like maybe these, and then some which are not. I'm going to skip that one, and then maybe these are both divisible by p. But a2x squared is markedly not divisible by p. All right, and it doesn't have to be a2, it's just we're going to use this as a stand-in for what's going to happen in general in the arguments. And let's say in g of x, we have some terms which are divisible by p, and some which are not. Let's say this one is, the next one's not, and then the next one is, and then maybe both of these are. All right, so where do we expect to find trouble in the array? Trouble in the sense of not being divisible by p. Well, we think probably the partial product we get here will not be divisible by p. And we know it won't be because if a2 is not divisible by p and b1 isn't, and p is after all prime, then the product a2, b1 cannot be divisible by p. But the thing that we have to verify is that there are other terms of the product that have the same degree, or I should say other partial products that have the same degree. This one has degree 3, but then so does this one, and so does one over here, and so does one up here. And I realize I'm going into parts of the diagram that are not completely determinate, but I could also fix that a little bit. I could make that slightly more visible there. All right, so here I would have b3 x to the third, and then up here I would have a3 x to the third, just in case that helps. All right, and I'm not going to render a verdict on whether a3 is or is not divisible by p, and the same with b3, because one thing that I know, without having to even worry about that, is that everything in this row is divisible by p, and everything in this row is divisible by p, and then everything in this column is divisible by p, by virtue of b not being divisible by p. This right here, the red circled box, this is the only partial product of degree 3 that's not divisible by p, or rather whose coefficient is not divisible by p. That's going to mean that the sum of all these is not divisible by p because everything else was. This was, and this was, but this wasn't. So the x cubed term of this product will not be divisible by p. Now the problem here is I have to free my thinking from anything about degree 3 specifically, because it may not be degree 3 that doesn't work out in the partial, or in the product of f of x and g of x. Nonetheless, this really holds the key to the reasoning. What I do is I march out, starting with the constant term of each polynomial, f of x and g of x, and I keep going until I find the lowest degree term on each of these that is not divisible by p. And how do I know that there is a term not divisible by p? Because I assumed that f of x and g of x are primitive. So each one has to have a coefficient not divisible by p. I'm going to look for the lowest degree one. All right, so that's the game plan. Let's see if we can write some of this up in the proof. All right, switch colors here. There we go. All right, so because f of x and g of x are primitive, there is a coefficient of each that is not divisible by p. So let a sub I and b sub j be the lowest degree coefficients of f of x and g of x respectively that are not divisible by p. All right, so we've got a sub I and b sub j. So what we're going to do now is we're going to let n equal I plus j, and I claim that c sub n is not divisible by p. Okay, now where am I getting that idea? Well, here's my thinking. In this example here, a2 was the lowest degree coefficient of f, not divisible by p, and b1 was the lowest degree coefficient of g, not divisible by p. And where did our not divisible by p coefficient of the product come from? Well, it came from multiplying this term times this term, where I got an x cubed. That x cubed, of course, the 3 is 2 plus 1. So I'm hoping that in general that reasoning is going to hold up. But of course, to prove this, I have to show attention to all of the other little pieces that make up c sub n. So we know by our definition of polynomial multiplication, c sub n is equal to the sum, and I'm running out of things I can use as an index. Gosh, let's say from r equals 0 to n. I apologize, it's kind of weird. So the sum from r equals 0 to n of a sub n minus r times b sub r. That's our coefficient c sub n. All right, so we know that that's true, and we know that this sum consists of three types of terms. So this sum has three types of terms. The first type is the one that we are super interested in. One of the terms is a sub n minus j, b sub j. And that's equal to a sub I, b sub j, because n minus j was equal to I. And this is not divisible by p, since p is prime. P does not divide a sub I, and p does not divide b sub j. Okay, so that kind we like. The others are kind of annoying, but we still have to pay attention to them. So the other ones are, number 2, a sub n minus r, b sub r, where r is less than j. Okay, but if r is less than j, then p divides b sub r, since b sub j was the first not divisible by p. Okay, so in other words, looking at our diagram, we defined this to be the first term or the lowest degree term of g of x not divisible by p. That means all previous ones are divisible by p. That's what we're looking at here, is we're looking at lower degree coefficients b sub r, which all have to be divisible by p by our minimality assumption. And then the third type is a sub n minus r, b sub r, where r is greater than j. So where r is greater than j, but then I claim p divides a sub n minus r. Since n minus r is less than n minus j, since r is greater than j, we're subtracting something bigger, should end up with something smaller. And by the way, n minus j was equal to I. And we assumed, there we go, and we assumed a sub I was the first coefficient of f of x, so this one right here, not divisible by p. Divisible by p. Okay, so it has three types of terms. This one here, which is not divisible by p. This one, which is divisible by p, so p divides this, and p divides all of these. So all of these together, all the coefficients here, all the coefficients here add up to something divisible by p, and then they get thrown off by this one term here. All right, so just to sum that up, so c sub n is the sum of a bunch of numbers, integers, divisible by p, and exactly one that isn't. So p does not divide c sub n, so p does not divide the GCD of all of the c's. And I think the last of those was c sub m. There we go. All right, therefore, p does not divide the content of f of x times g of x. And now we can sum up. There we go. So let's zoom out one last time. All right, closing argument. Therefore, the content, sorry, my pen is skipping like crazy, of f of x times g of x, there we go. The content of f of x times g of x is not divisible by any prime because p was arbitrary. So it must be 1. Thus, f of x times g of x is primitive. So this is a good example of a proof. The proof is hard to write down, but the hardness is not in the problem solving once we figured out everything here that's in this diagram. The difficulty is in figuring out how to take the idea of this diagram and translate it into something more general, but I think that we have managed to do that here. So anyway, I hope you enjoyed that, and we will talk later about what big theorem we can prove using this lemma. This is really a lemma to a bigger theorem. We will see.